Hey everyone, my name is Mohammed Ramshamel and we're from the Archangel Group. Today, we're diving into the fascinating world of turbofluid. Specifically, we're breaking down a highly insightful paper titled A Review on Performance and Optimization of Radial Flow Pump Impeller through CFD analysis. Ever wondered how the water gets to your tap or how massive industrial fluids are moved around? Chances are a centrifugal pump is doing the heavy lifting. But these aren't just simple machines. They are complex that demands precision engineering. Modern pump designers have faced a constant challenge. How to build a machine that are not only more efficient, but also quieter, more reliable, and ultimately more cost effective. It's a tough puzzle, especially with so many variables at play. And that's where advanced tools come in. Today we're focusing on a powerful technique, computational fluid dynamics or CFD. This paper shows us how CFD is revolutionizing pump design by cutting costs and boosting performance. So what exactly did this paper set out to achieve? The author focused on analyzing and optimizing a specific type of pump, a centrifugal radial flow pump. Their goal was to achieve its performance. The pump they studied was designed for a particular task to deliver 0.0074 cubic meter per second of water, pushing it to a height of 30 meters, all while running at a speed of 2,870 revolutions per minute. The core of the approach involved two major software tools. First, they used PTC Creo version 2.0 to model the pump's geometry. Then they brought in ANSYS CFX, specifically version 14.0, the crucial fluid flows analysis. Their strategy for optimization was smart. They first assessed the pump's performance with its original blade configuration. After that, they systematically varied the thickness of the blade to see how it impacts the pump's overall efficiency and performance.
Let's quickly cover the fundamentals of a centrifugal pump. At its core, it has an impeller that spins inside a casing, drawing fluid through a suction pipe and pushing it out a delivery pipe. The basic principle is converting mechanical energy into pressure energy using centrifugal force, creating a force vortex that raises the liquid's pressure head. However, pumps aren't perfect. They experience various losses, including mechanical friction, disfriction, and leakage. These losses impact the pump's overall effectiveness. To measure this, we look at different efficiencies: manometric, mechanical, and overall efficiency. This tells us how well the pump converts input power into useful fluid energy. Finally, characteristic curves are essential tools for engineers. They help us predict how the pump will perform under varying conditions of head, power, and flow rate.
Let's look at the research process outlined in the paper. The methodology followed a clear flowchart starting with initial design, moving through geometry and mesh generation, pre-processing, solving, post-processing, and iterative check until an optimal design was reached. The impeller itself had very specific design parameters. For instance, it had a specific speed of 19, an outer diameter of 171 mm, an inner diameter of 66 mm. The blade angle at the outlet and inlet were approximately 28.9 degree and 22.9 degree respectively. The volute casing, which collects the fluid from the impeller, also had precise design calculation. For example, the mean velocity in the volute was determined to be 6.793 meter per second. Now, for the CFD simulation setup, accuracy is the key. The numerical computations were performed under the steady state condition. The impeller domain was treated as a rotating frame of references with a rotational speed of 2,870 rpm. At the inlet, they set an atmospheric pressure of 1 atm, and at the outlet a discharge of 0.0074 cubic meter per second. The working fluid was water at 25 degrees Celsius, and for turbulent modeling, they utilized the KFC model with a 5% turbulent intensity. And finally, the meshing process was extensive. The pump assembly was broken down into a staggering number of elements and nodes for the NC simulation. Specifically, the mesh comprised over 5.8 million total elements and 1.1 million total nodes, ensuring high fidelity in the simulation.
Now, for the key findings, the CFD analysis revealed a significant outcome. The pump efficiency increased by 2% for the optimized design. This improvement was largely attributed to optimizing the blade configuration. Specifically, the study found that 8 blades appeared to be the optimal number, leading to an approximate 1.5% increase in efficiency at its peak. CFD also provided powerful visual insights. We can see velocity stream contours in figure 5.2 showing fluid movement and pressure contours in figure 5.3 illustrating pressure distribution. These visuals are crucial for understanding and refining the pump's performance.
For conclusion, computational fluid dynamics (CFD) is a powerful and indispensable tool for simulating, analyzing, and optimizing the performance of radial flow pumps, enabling engineers to visualize complex internal flows, reduce design iterations, and enhance overall efficiency with greater precision and confidence. For the next part is practical impact. One of the practical impact is the skill of operation magnifies impact. In energy-intensive industries such as power generation, manufacturing, or transportation, operations often involve massive energy inputs. A small percentage improved in efficiency can result in large absolute energy savings. For example, if a power plant consumes 1 million megawatt hours annually, a 2% efficiency improvement saves 20,000 megawatt hours. It is enough to power thousands of homes. For the next one is the cost saving accumulate. Energy costs are a major operating expense. A slight improvement in efficiency directly translates to reduced fuel or electricity costs over time. Then, it can reduce environmental impact. This can increase efficiency means less fuel burn and fewer emissions such as carbon dioxide and sulfur dioxide per unit of output. Even modest efficiency gains contribute significantly to climate goals and emission reduction mandates. This is especially critical in sectors with high carbon footprints like cement, steel, or aviation. For the regulatory and compliance benefits, many regions have strict energy efficiency or emission standards. Improving efficiency even slightly can be the difference between compliance and costly penalties or restrictions. Efficiency improvement in one component can reduce strain on related systems, leading to cascading benefits. Less heat generated meaning lower cooling costs. Smaller generators or motors means that less wear, longer life, and lower maintenance. Energy efficiency is a driver of competitiveness. Firms that operate more efficiently can offer lower prices, increase margins, or reinvest savings into innovation. Less energy input per unit output means lower demand on the grid, greater resilience during peak times or supply shortages, better alignment with variable renewable energy sources. For future work or future research, promising directions include exploring additional design parameters such as impeller geometry or blade angles, investigating performance across different pump types, for example, axial or mixed flow, and conducting transient flow analysis to capture unsteady effects and dynamic operating conditions. This area could further optimize pump performance and broaden the applicability of simulation tools in industrial settings. For the last part is call to action. Be sure to check out the full paper for detailed findings and insights. The world of fluid dynamics and computational modeling is full of innovation. There's a way more to discover. That's all.
Hello, my name is Muhammad Shamil, and for this class, I want to say that I very enjoy this class because I learned a lot about turbo fluid, especially on the turbo itself. Since I am a very fan of a car, and learning about turbo makes me wonder how I can do an improvement on turbo on the car itself. That's all from me. Thank you.
During the PMP session for Turbo class, I had both good and hard experiences. The good part was that I enjoyed the group discussions. They helped me understand more about how turbines and compressors work. I also like learning about how they are used in real life. But I also had some problems. Some topics were hard to understand, like the formulas and the velocity triangles. Sometimes I felt confused. Luckily, Dr. Yusmadi and my friends helped explain things, so I slowly got better. Overall, the PMP session helped me learn more and made me more confident. I also learned how to work in a team, which is very useful for my future.
I had a great experience learning in the turbo machinery class. The lessons were clear and the real-world example helped me understand how turbine and compressor works. I also enjoyed the group discussion and assignments. It made the learning more interactive and practical. Overall, it was a very valuable class. Thank you, Dr. Yusmadi.
I think that the PDB class for the turbo machinery is interesting because the doctor explained the turbo machinery slide in different ways, and he give us exercise and quiz so that we can understand the chapter more.